We are very grateful today to Peter Todd, Bitcoin developer from Canada and the founder of Open Timestamps. Today, he will continue to tell us about his project. Thank you.
Yeah, thank you. First of all, I'll go start with a presentation I already had, and you can just pretend that rather than Lugano Plan B, it says Kiev, and rather than 2023, it says 2025. But this is a presentation I gave 2 years ago based on how we use my Open Timestamps project to go timestamp an election. And in this case, that was the Guatemalan election. More recently, parts of the US election have been timestamped. But I think if I'm going to start with that, I mean, interesting question here is in this audience, first of all, how many people have heard of timestamping? Since yesterday. Okay, so technically yes. What about open timestamps? Probably since yesterday. Well, let's get started then. So, what is a timestamp? Well, one common way to talk about it is carbon dating for data. And my understanding is, the audience here might be a little more developer-ish, but maybe one way to go talk about it is say, like, why do you timestamp data? I mean, why do you care about the so-called carbon dating thing? And I would say that really it's because bad guys don't have time machines. So if you can show that data existed in the past, you can rule out things happening to that data after when you proved it existed. There's lots of examples of this. Very simple one could be, imagine you have a digital signature on something. Of course, surely if someone steals the private keys to this, they can create fake signatures. How do you go prove that the digital signature was real? Well, you show that it existed in the past, prior to when you think the compromise might have happened. And there's your example. I might be a little more polished when I've actually given this, like recently, but I'll see if I remember what order the slides are in. But this is a good example of exactly what I talked about. And in fact, this is an example of us screwing up. So this, you probably can't see this easily, but that says Peter Wool at the top, and this is a git commit from Bitcoin Core. And what happened quite a few years ago was Peter Wool's private keys got compromised. And if you go look in the GitHub repo for Bitcoin Core, there are tons of these signatures from Peter Wool. Now, if we had timestamps from then, and I'd have to double check, I think the compromise happened after Open Timestamps was made, but probably before the first timestamp ever got in Bitcoin Core. But anyway, assuming we had, this would be a perfect example of this. You'd be able to say, hey, we know this key was used to go sign this git commit on, what would that be, say, August 2015. We know the compromise happened, say, 2016. Well, that's all you need to say, actually, this is not potentially compromised. This is legit. And here's a 2017 example, signed by myself, Peter Todd. And in this case, this is after Open Timestamps was created. And if you go look at a little down there, you'll see something you probably won't see on a Git log, which is OTS, got 2 attestation success. Bitcoin attests this data existed as of February 19, 2017. So we have some kind of proof saying, hey, this signature, and of course everything it signed, existed as of February 19, 2017. Well, if I now say, oh, you know what? Someone went and grabbed my laptop there and stole my private keys, this thing would be fine, as long as I can narrow down when that happened. Now, another example of this is a project called Proof Mode. And in fact, I have a better example that came about actually quite recently. But essentially, there's lots of data in general where if you can say it hasn't been changed since then, often the meaning of the data only becomes apparent later. Proof Mode, as an example, is an Android app which lets you timestamp all of your photos and videos. It also saves some other data around this, but the main purpose of this is it's meant to let you capture things with more evidence that what you captured was real. And more recently, Bellingcat, I don't know if you know of them, but their community organization that's basically doing a lot of documentation of things related to war crimes, things related to war in general, and so on. And they also added open timestamp support to their main archiver. And again, what's the rationale there? Well, if I can say that, this claimed, say, Telegram archive was created as of such and such a time, provided that you can go rule out there being a reason to modify it before the timestamp, you get a much better certainty that it's real. Now, this isn't always true. I mean, you can imagine, for instance, if you're taking a photo that's kind of born important, something that obviously from the beginning of when it was created had importance, well, maybe it was fake to begin with. But there are many times when you can rule this out with timestamps. So under the hood, I mean, how does all this work? Well, how many of you know what a hash function is? Or at least think you do. All right, fair number. So timestamping generalizes hash functions a bit and talks about commitment operations. And a commitment operation, mathematically, is basically a proof that one message existed prior to another message. And when I say message, I just mean, bytes, digital data. So if you can say that one message certainly existed prior to another message, you can say that, depending, of course, usually how this exists, that one message committed to another. So the really trivial example of a commitment operation is like append and prepend, because you take one message, you add something to it, or to either the beginning or the end, and thus the output of this function included the input. So obviously the output proves that the input must have existed. I mean, it's partly the same thing. This is trivial, but it's still useful and it's important, because the other commitment operation, well, there's your hello world, is hash functions. And hash functions are kind of magical because they take any sized input and create an output of a fixed size. Now, why can this work? I mean, how on earth could something commit to something if the output is fixed? Well, this is where we go from mathematical proof to really sort of energy or computational proof. Because obviously, that output, I mean, there's only so many numbers that length. And if the input can be any size, surely there will be two messages with the same output, right? But if the output is big enough, it's computationally infeasible to find it out. Well, SHA-256 has 256 bits in the output. And if you look at the number 2 to the power of 256, it is so unfathomably large that it's just infeasible for us to ever find a SHA-256 collision. Now if you're familiar with like the birthday paradox, you might know a little bit about this. Since there's basically, if you're trying to create SHA-256 digests, the bound on it is essentially if you create 2 to the power of 128, there's a 50-50 chance that two of them will collide, two of them will have the same digest. But the amount of effort it takes to even do 2 to the power of 128 is absurd. It's just not going to happen. So we can use this as a commitment operation because the input maps to the output randomly. It's as though you had some magical database in the sky where you just go and ask it for a new number every time you came up with a new message. And since it's random, there is no shortcut to finding two with the same output. You just have to keep on guessing. Now, of course, if you know a bit about Bitcoin, you might say, well, of course, this is how Bitcoin itself works. I mean, Bitcoin's proof of work is based on something like this, by running this sort of lottery till you get digests with the right properties. But in open timestamps, we just use a simple way, which is say, yeah, that's also a valid commitment operation. So we have two valid classes of commitment operations. We have hashing, and we have append and prepend. Well, what can we do with that? Well, Merkle trees. So if you have a lot of different bits of data, you can hash them, you get a bunch of hash digests, and then you can take these hash digests and append and prepend them together, or concatenate them together. Well, we concatenate them, and then you can repeat this over again and concatenate them again. And because we're taking many things, turning them into 256-bit numbers, concatenating them, turning them back into 256-bit numbers, this scales. We can take any amount of data and get a single top digest, top hash, if you want to call it that. And there are mathematical proofs you can create that show that anything at the bottom, there's a commitment operation path to the top. Thus, if anything at the bottom changed, the top would have to change too. Let's see if I remember what slide this is. All right, so what can you do with this? Well, guard time is a very old time-stamping solution. I think they've got their start in like 1999 or something, 2000-ish, something around then. And they were one of the first people to really offer timestamping as a service. Of course, the catch with all this is, the Merkle tree part's easy. And guard time under the hood uses Merkle trees. But how do you go and anchor this to time itself? Well, right here is a newspaper, July 17th, 2009, a couple months after the first Bitcoin block. And guard time has gone and paid the newspaper to go put their hash digest for their massive timestamping service. And guard time, it had sort of it has two elements to it. One is guard time itself will create a signature claiming that, hey, we signed this thing as of this time. But then the other half of it was they would go stick things in newspapers saying, hey, if you really want to, you can go to your local libraries, find a copy of these newspapers, and verify that these numbers match. And that is your anchoring to time. Not only are we showing data existed before, one piece of data existed before another piece, now we're saying, hey, we actually can say when that data existed in human readable, human understandable time. Of course, this kind of sucks. Who the hell wants to go verify something by going down to like local newspaper? It's ridiculous. And also, I don't know, maybe someone's changed that. Like, how do you really know? Newspapers aren't that widely witnessed. You could go to a couple different libraries, but it raises questions. So, open timestamps, we do basically that, but you use Bitcoin. Because fortunately for us, Bitcoin blocks, in the Bitcoin block header, there is a field, end time, and it's kind of complex how it really works, but roughly speaking, it's fair to say that when a block is created, the time it was created is put in the block header. Now, of course, you might ask the question, what was the incentive for miners to actually do this accurately? And that is an interesting question. There's a lot of nuance about how time works in Bitcoin, and I'm not going to say it's that accurate, but the important thing is it's accurate enough. I remember when we were talking about timestamp use cases, a lot of them, if you can nail down to the nearest month, you're doing pretty well. Like we're talking about, PGP keys and signatures. Usually, the vast majority of use, if you can say, hey, something existed as of 1 month, that's good enough. And with Bitcoin, it's quite fair to say miners have very decent incentives to set the times in their block headers to at least the correct day. More accurate than that is an interesting discussion, but certainly to within the nearest day. Thus, open timestamps, well, we can go take people's data, create Merkle trees, stick it in Bitcoin transactions, and then create proofs. And I'll go talk more in detail about how this actually works. So if I remember correctly, I didn't in this slideshow. But from here, I think we can, if I remember correctly, this is where we start talking about the election. Yeah. So, as for the election part, well, what was going on there? So this is going back to the Guatemalan presidential election in 2023. And that was it's probably at the highest profile use of open timestamps to date. And, like most elections, it's a paper ballot system. People go and, get their ballots, put X's on where they want, the ballots go into boxes, and so on. And it's quite an analog thing. Actually, I wonder, does Ukraine use the system too? Do you guys recognize what this is? You don't, but you do know what it is. Yeah. So I love this system. So this is a very clever idea a lot of countries have, which is obviously you don't want people voting more than once. So you just go have them stick their fingers into ink. And if they have ink on their fingers, you're not allowed to vote. And then hilariously, because of course bureaucracy has to have a solution to this, if your finger is amputated, well, then you do this finger. And if this finger is amputated, you do this finger. And they have a whole list of rules around which body part they do based on which order of amputations. But yeah, enough of that. But anyway, point is, it's a very analog process, even right down to putting people's fingers in ink. And the output of that analog process per ballot station is this. It's a sheet summing up the votes. Because, of course, like most elections, Guatemala's voting is anonymous. You put your vote in a ballot box, and there's no identity attached to it. So at some point, we got to open up these boxes, sum up who voted for who, and you write them down on a sheet. And there's two things that happen to these sheets. One, of course, is that they go into secure storage. But the other one is that they get scanned. Because at some point, you got to tally up the votes across many different ballot stations. So in this case, in Guatemala, this is sort of the beginning of digitization. These sheets are actually scanned in, and there's software on a dedicated computer system that reports to a central database, here was the voting that happened in this place. Now, there's a whole secondary system of people literally making phone calls, people recording journalists. I mean, there's tons of checks and balances here. But the part that I was involved in, my client, Simple Proof, came up with, they were involved in this digitization system. Is right where this happened, that's where you added a timestamp. In fact, there's me right there. And it was kind of a funny setup, because I did get the official election worker ID badge, and we all wound up in the sort of central party area, if you will. Because, of course, one of the ways that we make this process secure is through visibility, which in this case meant renting a gigantic hall in a hotel in downtown Guatemala City and having everyone just show up. And, like most elections, there's a ton of pomp and ceremony. This was actually the moment when they officially started the election, when they officially started the counting, if you will. And they actually went and timestamped the official documents, which was kind of a terrifying thing when you realize, oh shit, no one actually told them Bitcoin blocks take like 10 minutes at least, because they're all waiting on us on live TV for a Bitcoin confirmation until finally someone told them, yeah, maybe just move on to the next part. But, it is what it is. So what happened then? I mean, we have these tally sheets. We have these timestamps. Well, and I'm not Guatemalan, so I'm kind of repeating this secondhand, and I'm not going to get every detail quite right. But roughly speaking, what happened was accusations of election fraud, but not in the obvious way, because the outcome of that election was that the ruling party lost. In the ruling party, it's alleged, I'm not sure if it's actually proven in court yet, but there's certainly a lot of evidence for it, they deliberately did election fraud in all area. Because, this paper ballot system, you need manpower to change the ballots. So in one area, I believe it was Guatemala, parts of Guatemala City, if I remember correctly, they literally just sent their thugs around to grab the ballot boxes and take them away. And let's see if I actually have it. So it was quite funny, because a lot of the ballot sheets that then came back, they would literally have the numbers crossed out, new numbers written next to them, with no explanation of why the hell the numbers changed. And what we got was a bunch of timestamps But in the vast majority of ballot locations, the timestamps were what you'd expect. Election stopped, things start coming in like 30 minutes to an hour later, and it's what you'd expect. In the places where fraud was alleged, the timestamps were hours later. I mean, even like the next day. And remember how I said the ruling party here? The curious thing about this was the ruling party wasn't trying to throw the election. They didn't have the manpower to do it. They couldn't alter enough ballots to actually win. But what they could do is they could say there was widespread election fraud, thus we should throw the election out, reschedule a new one in 6 months, and then they get 6 more months campaigning. That was actually what I'm told was the goal there. And by proving that the vast majority of ballots were counted when you expected them to be counted, we were able to go say, hey, actually this election was mostly done correctly. Let's do a rerun in this small area. And sure enough, the rerun didn't really affect the results, and the ruling party lost, and new people got in. The other thing that happened was all these scans, due to widespread misconfiguration, a lot of them had the wrong time zone. Like literally the computers that did this, people screwed up on the time zone. And if you screw up on the time zone, NTP doesn't work properly, and then you wind up with a whole lot of stuff that was forward dated. Now, timestamping doesn't quite help you there, but at least provided yet another piece of evidence to say, hey, this was just a screw up. It really doesn't matter. This is irrelevant. The data was still timestamped when you'd expect it to be. In theory, maybe hypothetically it was created before, but it's an election. You have literally thousands of witnesses saying, yeah, everything went smoothly, except in the places where, yeah, armed thugs went and grabbed the boxes and returned them 12 hours later. And hopefully, this will all be done next election, but we'll see what happens. My client who actually performed all this stuff, they apparently are still working on getting paid by the Guatemalan government 2 years later. But, that is what it is. It's not really my problem. And for the U.S. election, the role of open timestamps was similar. There was one small county where they did basically the same thing for all of their individual ballot locations. And in that case, no one accused anyone of anything. So didn't exactly make the news, but technically they were the second major government to do timestamping. So that's that presentation. And after all this, you think you understand why timestamping is useful? Maybe a little bit. I mean, it's not that useful, let's be honest here, but it serves a role. And I think I could make a good argument to say that any circumstance where you have data that you're archiving for later, you might as well timestamp it. Because timestamping is a process that should at least be essentially free. Why? Well, because Merkle trees, you can put any amount of stuff in them. Indeed, a couple years back, actually quite a few years back these now, I went and timestamped essentially all of the Internet Archive. I just downloaded their metadata, which had hashes in it. And this was like, a terabyte or two of metadata. Not the data, just the metadata. Put them into a gigantic Merkle tree of 500 million items and timestamped it. It's really not that hard. I kind of wish I was able to convince Internet Archive to do this further, but unfortunately they heard the word Bitcoin and a couple people there said, nope, we're not going to have anything to do with this. But that's that. So now I can go switch to, I think, what I wanted to go show on my laptop, which is, okay, I told you about how Merkle trees work. I told you about how this stuff all is good. The catch is, until recently, the software to actually do this in a scalable way didn't exist. Because remember, let's go back a bit. So, how does open timestamps actually work? Like, what's really going on here? It's not enough to just say, oh, create Merkle trees. How do we actually create the Merkle trees? A lot more use showed up than I was expecting. But, so, let's say you have a piece of data for me. All right? A lovely circular piece of data. Let's say he has a piece of data for me. Another lovely circular bit of data. Obviously, we can build this up into a Merkle tree. Now, our goal with open timestamps is you don't want to have to wait for a Bitcoin block to actually get your proof back. As an example, as you saw earlier, I have support for open timestamps for Git commits. No one wants to do Git commit, sign, and then wait for 3 hours for me to finally timestamp the transaction. That's absurd. So how do we fix this? Well, open timestamps has this concept of a calendar. Yeah, you can't read it. Whatever. It says calendar. Calendar as in the word calendar. A sort of a set of time-related things. But the important thing is these calendars, they make a promise to you, which is they will timestamp your data later. So to a first approximation, you could say, well, you submit to me a digest, and I make a promise I will timestamp you that digest later, and you will be able to ask me for a full proof going all the way up to a Bitcoin header. All right. What's wrong with that, though? So keep in mind, the calendar is promising to you that there will be a timestamp later. It doesn't say there will be timestamp now. So if you, in open timestamps, create a timestamp right now, you can't immediately verify it because a Bitcoin transaction hasn't happened. So that seems simple enough. But the catch is, if I make this promise, what happens if everyone on this planet wants to timestamp something? All right? I could have 10 billion different digests to be timestamped all at once. That's totally infeasible. I'm not going to store 10 billion, SHA-256 digests every second. So instead what I do is the calendar has the idea of a per second commitment. So every second, I take everyone in the whole world who is submitting digest for timestamping, and you build, a giant Merkle tree of this. Yeah, something like that. You get the idea. So everything below that dotted line is ephemeral, right? This is something I created in 1 second, but the calendar doesn't store any of that data. Instead, what we do is, again, let's say this is your piece of data, your digest. Instead, you store this part. You store the path up the Merkle tree to that per second commitment. Similarly, if someone else they might have this path. And if I had my laptop, I would have gone and showed you what this actually looks like. But it's basically just, again, a set of commitment operations, append, prepend, hash, et cetera, et cetera, et cetera. And mathematically, this means you have proof from here to here. And then later, the calendar takes all of this stuff, builds a giant Merkle tree of this, and then this goes in a Bitcoin transaction, which eventually goes in a Bitcoin block. And what the calendar does is it stores all of this data, right? Everything beyond 1 second. So again, the calendar has committed that it will timestamp it. You have saved enough data to get to the commitment, and in the future, eventually we get a timestamp, and then that's good to go. All right. Can you see a problem with this? Well, who does this part? Right. In the first software implementation, the calendar did this. The calendar accepted requests, created a giant Merkle tree every second, save the commitment. The catch is, can one computer do 10 billion timestamps per second? Absolutely not. It just can't. So we can solve this problem, as we solve everything in computer science, with a level of indirection. Rather than have one Merkle tree, we can just add another one, right? We can say, let's take multiple aggregators that accept connections. So imagine if everyone in the front row ran one of these aggregators. Every, say 0.1 seconds, you're building a Merkle tree of everything that everyone else submitted to you. And then every 0.1 seconds, you submit your digest for that 0.1 second interval to me. All right. And then I go build, Merkle tree of that. And then finally, that gets to the commitment. And because it's just Merkle trees, from the point of view of someone timestamping something, it doesn't really matter that there was an additional step in between, right? It's still all just hashes. And in practice, so the recent innovation in open timestamp scalability has been implement this. My client, Simple Proof, I told them about this issue back in 2023, and they basically said, okay, well, we'll look for funding. They finally got some funding to go fix it, so I finally wrote the software that actually does this, and that's called Foxglove. Foxglove is a species of tree that is notable for growing very fast. And essentially now, anyone can run this Foxglove software and make as many timestamps as you want, and then submit them upstream. So we're taking levels of timestamping, and if you needed more, you can always just add more levels to this. So that's all well and good. But can you still see a problem with this? Like, imagine that you use this in practice. What's the thing that's going to fail when everyone and their dog wants timestamp data? All right, but so we've solved things. So we've solved resources for one thing. All right, we've solved how do we make a lot of timestamps. What's the other thing we have to solve? Well, that's something we can go solve. But there's actually a simpler thing to solve. Remember this part here. How exactly do we go scale this thing? Because later, let's say 10 billion people create a timestamp in 1 second. That means in the future, if they all verify their timestamp, 10 billion people are going to ask for this data. And at the moment, if everyone asked for their timestamp data, open timestamps would immediately fail.
Directly Bitcoin, they cannot ask calendar or open timestamp.
Well, this is the thing. They don't have the data to go to Bitcoin. That's the problem. Because when you create a timestamp in open timestamps, all you get is this data initially, right? In the future, you can ask for this data and you'll get it. Or you can make a copy of all this data. But I don't actually have a system to give everyone this data quickly. This part doesn't scale. We can create timestamps, and certainly if everyone tried to verify their timestamps, that's an acceptable problem because at least we can still create them. But currently, the verification doesn't actually work properly because it doesn't scale. Now, you might ask the question, well, okay, why does Bitcoin work? Well, in Bitcoin, we copy the data around, right? You go find a block, you feel really lucky about it, you're now a rich man, and you're so excited about this, you give everyone a copy of the block. And because we can copy that data around, we're all good to go. But the problem with open timestamps right now is there isn't a blockchain involved. It's just a database. And copying databases is actually kind of an ugly process. How am I working on fixing this? Well, in the long run, I want to go and actually make open timestamps be a blockchain of its own. And the reason is not because blockchains are brilliant or all this, but actually a very boring one, which is Bitcoin timestamps aren't that accurate. Now, remember I told you earlier how you can kind of certainly trust them to within a day or so. The issue really comes down to what is the incentive for a Bitcoin miner to set the correct time. And I can go tell you about, there's basically 2 rules in Bitcoin. The first rule related to time is that if you run a node, you will not accept a block more than 2 hours in the future. And then the second rule is you will not accept a block with a time less than the median of the past 10 blocks, past 11 blocks. Yeah, I may have forgotten the number, but median of a past certain amount. So this constrains time in two directions. But it doesn't really, though. Like, it's actually kind of not clear. And one of the issues here is, I mean, let's suppose that you're a miner and you find a block. Is it always in your incentive to have everyone accept your block as valid? Well, that's not that clear. Like, certainly, if he found a block, I'm pretty sure he doesn't run a multi-petahash, exahash, whatever it is, mining operation. I think he's just one dude. And if he's just one dude, his chance of finding another block soon after is very low. So he needs everyone in the world to know about his block right away so they start building on it. All right? Because remember, the definition of a valid block, sort of step zero, is other people have to know about it. All right? If they don't know about it, who cares if it's valid? I mean, it doesn't really matter. And of course, the second bit being, well, the most work chain wins. But that advertising thing is the important thing. Now, the catch is, imagine you have a miner with, say, 40% of the Bitcoin hash power. They can earn more money relative to their competitors by having their blocks not propagate fully. Because they're quite likely to find 2 blocks in a row. He's not going to find 2 blocks in a row, but like F2 pool, they're a pretty good chance they're going to find 2 blocks in a row. And if they find 2 blocks in a row, that 2 blocks in a row can beat other people finding 1. And I could give a 30-minute talk on the nuance of this, but what you need to know is this time rule around 2 hours, it's not really clear how that plays out if miners start having incentives to like screw up the Bitcoin community. If miners start pushing this limit, maybe like blocks time start getting dated further and do weird things. Now, for open timestamps, fortunately, a block being further into the future isn't actually so bad, right? Because remember, what's the definition of a timestamp? We're saying data existed in the past. If we forward date the data, we're creating a weaker timestamp that proves less. Thus, that's actually probably okay. But if miners start doing this, it's not really clear what happens to Bitcoin time in general. Like maybe people remove some of the limits. It's really unknown. And of course, the second thing being this median time passed. Well, if everyone wants to manipulate timestamps, they could backdate their blocks. And there's nothing really stopping a lot of hash power from just putting the number and putting the date in the past. And part of why there's nothing stopping them is like they can also play games with saying, well, now the blocks are, sort of this date into the future. So yeah, it's a bit of a mess. So something I would have loved to show you is the thing with timestamping is we can add additional proof. Now, one piece of additional proof can be finding many different things and timestamping them. There's something called NIST, project of mine called NIST Inject, which takes many different sources of time, things like the NIST random beacon, which is a number that NIST promises, National Institute of something or another. Anyway, it's a U.S. government institution, and they promise that they will release random numbers at certain times in the future. And these are numbers which could not have been known prior to a time. Thus, if you can show that a Bitcoin block depended on them, you constrain when the block could have been created. You can also do things like take, say, Ethereum chain and timestamp it in Bitcoin. But finally, getting back to where I was beginning, open timestamps can also just go and start claiming, hey, we're going to sign things too. And something I would have loved to show you here was how open timestamps actually kind of already does this. Because like at this point, right, where I have those commitments, the way the data actually works is you have a digest. You actually have a 32-bit integer, which just happens to be the current time, and you have a HMAC. And an HMAC is created by hashing a private key with something. So this is a hash derived from this with a private key. Now, the HMAC by itself doesn't really mean anything. But if I reveal to you later the secret key that went into this, I can say, hey, this was actually created as of a specific time, as of this time. Now, why does Open Timestamps have this? Well, actually just for backups. Like if I lose all my data, I want a way of validating a copy that I get from somewhere else. This isn't meant to be used for time, but in the future, I would like to go switch this with a proper signature and be able to actually give some better guarantees on what Bitcoin miners do. Really, it'd be like redundancy. So if I do that, well, how do I go and do something useful with this? Well, the obvious thing to do is make this into an actual chain. And indeed, you look way back in the past, like the term blockchain actually dates back to timestamping. Why does it date back to timestamping? Well, early timestamping systems like guard time are trusted, and they really want to be able to convince you that they operated their service honestly. Well, part of being honest is that there really should be like one single continuous set of signed timestamps. And anyone should be able to go check them, and we should all be able to just verify that they all happened when they should have. So in the long run, I want to get this into open timestamps. But there's an ugly catch with this, which is, let's say I do all this. How the heck do I actually go synchronize like this piece of data across multiple people? Now in Bitcoin, we have the blockchain data structure, but the blockchain data structure is kind of imaginary. All right, it's how the cryptography works. It's not how the data itself actually exists. All right, on Bitcoin right now we use, I hope I get this right, I believe it's one of either LevelDB or LLDB. Someone should double check this. But it's just a key value database, and the keys in Bitcoin are basically speaking block hashes, and the values are the serialized blocks themselves. I'd have to double check if I'm actually correct on this, but I believe that's roughly correct. But being databases, it's still kind of annoying to actually synchronize. And with Bitcoin, this is kind of okay because reorgs can happen, right? It's because miners are not consensus directly. You have to interpret consensus, thus the blockchain can go backwards and forwards again and so on. But with open timestamps, I want to go do something a bit more straightforward with this, which is I want to go have a very simple append-only file format. And I'm already doing this to a degree, which is, remember how we're talking about the commitments? Well, in the open timestamp server, the way that all of the commitments are stored is in a file called the journal. And the journal is just, I think it's, it'd be 40 bytes. 40 bytes, 40 bytes. So every second, we're writing 40 more bytes to this file, which means that the file can have the append-only bit set. So in Linux, you can go set a bit in the directory saying a file can only be opened for appending data. You cannot write earlier data. Earlier data is just immutable. Under the hood, that's not actually how it works, but Linux provides this API that lets it work that way. And with the journal, I have very good certainty that if I've ever made a commitment to timestamping something, I will have that commitment forever, assuming Linux doesn't screw up, and we're good to go. So I like this idea. It's very nice. But I want to go further with this, which is I want to go and have a way of using this as a database itself. All right? Because in open timestamps right now, the journal only stores the commitments. The timestamps themselves are just in a LevelDB database. And they're key, it's key value, where the keys are messages and the value is how do you further timestamp that message. But LevelDB is kind of complex, and there's a program that lets any of you back up a given open timestamps calendar. But I tell you, like, I've had it running on my laptop for literally weeks. And that's how long it takes to synchronize one to the other. It's just a very slow process. It would be so much faster if I could somehow just take a big file and just download it. So, how can we go make a file format where you can find arbitrary data in it, but you can also just write the data to the end? Well, I came up with this idea, which I'm calling a breccia, which is a geological term for a type of rock that's formed by having big broken pieces of rock that all kind of get jammed together, and like the spaces are filled with very fine rocks. And this breccia concept is kind of like that, which is to say, what if we divide a file up into words, right? 8-byte words. And we create marks, special words that you can find later, where you can find the beginning and end of data blobs. So it's a file. We put in blobs of data, arbitrary data, and then we need a mechanism to find the blobs of data later. Now this is actually, I've tested this with a few friends of mine. This is quite a hard problem to come up to solve from scratch. How would you figure out a mark that you can just find arbitrarily, even though the rest of the data could be anything? Got some ideas? Like, maybe one way is, what if the mark's like big enough and random so it's very unlikely that other data would match that mark, right? Like you could imagine a file structure where you just take a big number, like 32 bytes, pick a random thing. The chance of any other data matching it is so low, it's essentially zero. It's a very good idea. But if someone knows what the secret mark is, they can intentionally put in data that matches it. So that's out. I mean, certainly this is very easy if you can say the data has some property that's different than the marks. Like you'd imagine a file format where like the data is text and the marks are binary. That's very easy. But again, we want arbitrary data. So the solution I came up with was you take the number, the index number of the word. So 0, 1, 2, 3, 4, yada, yada, yada. And you say that the mark is the index of the word in the file. So if you want to write a mark here to indicate the beginning of data, you write 2 in there. 2, 3, 4, 5, 6. And you could write 6 there. And then everything in between here is just normal data. And the only trick there is, well, when you write the data to the file, you just check, do any of these words have a collision with the marks? And if they do, you just shift them over. You just write extra padding. Like you'd imagine if I wanted to write the word 3 here as the first bit of my blob of data, well, put a 3 there and just shift the whole thing over 1. So now 3, whatever, that'd be 7. All right, so why is this useful? Well, we can write arbitrary blobs of data to a file. We can get back the offset so we know where we put it. But then the key thing is, because we can find the beginning of a blob anywhere in the file through this mark thing, you can now do binary search. And the beauty of open timestamps is everything's related to time, and time only moves forward. So what probably will be implemented, but I haven't finished this yet, which is when I switch to this, when you create a digest, run the calendars, eventually you'll get to a commitment. The commitment will have a certain number of bytes at the beginning stating what time the commitment was made. That gets written as a blob. And now when you go back to me and say, hey, where's my timestamp? You would do binary search, finding, first of all, the commitment itself, which you can do because they're labeled in order. And then once you go find it, you can find the timestamp by just reading a bit more of the file and looking for the right timestamp. And I think this will work. Haven't implemented it yet, but I think it will work. And if anyone thinks it doesn't, I would love to know why, because you could save me a lot of work. But I think that covers it. I think that is my timestamping solution, how it actually scales right now, how it doesn't actually scale that well, how I want to go scale it, which is this. And obviously, once we have a append-only data structure, it's dead easy to just go and let everyone get a copy of it. I mean, like everything else in, web systems, I can just add caching until it works. And with that, thank you.